So for week 6, we're going to tackle the chapter of capacitor and inductor. So we'll start with the first part of the video on capacitor, and then we'll go into the topic of inductor. So let's begin with capacitor. So what's make a capacitor? Basically, capacitor is made of two basic components. The two components are basically the first one is conductive plates, right? Two conductive plates, and in between the conductive plates we will have the second part, which is the what we call a dielectric. So what is a dielectric? Dielectric, so the component here in the middle. So a dielectric is basically a component that doesn't conduct electricity, right? So it is a component that separates between the two conductive plates, which will later I'll explain how it works. So basically, when we look at the capacitor that you have in the market or you're using in the lab, they look cylindrical. Most of them are cylindrical, except for some of them. For example, here we see something that looks like a squarish plate, but others are these are plates, these are plates, these are plates, but others are usually cylindrical. So what happened? What's the difference with what I've explained here? What I've explained is basically two conductive plates, but now it's not a plate, it's a cylinder. So basically it's a sheet of conductive plates that are rolled into a cylindrical form, right? So that's what we have inside here. So how does a capacitor, what's the basic principle of operations of a capacitor? So to look at that, let me introduce the notion of capacitance first. So what is capacitance? Capacitance is the unit that tells us how many charge can a capacitor store, right? So capacitance is measured in farad, and it measures, what does it measure? It measures the quantity of charge that can be stored over the voltage that's applied to across the terminal of your capacitor. So for example, imagine if we apply a certain value of voltage across the capacitor, there will be a certain amount of charge that can be stored in that capacitor. So basically, capacitor acts like a battery that can store charges, but the stored charges divided by the voltage is what we call a capacitance. So the value of capacitance depends on depends on multiple things. For example, it can depends on the geometry of the capacitor. It can depends on the material of your plates and your dielectric. It can depends, of course, on various geometrical parameters such as the distance between the plates, the size of the plates, and so on and so forth. Right. So now we're going to look at the basic principle of operations of a capacitor. Okay, so let's imagine we have a capacitor. So we know that a capacitor is basically two plates, right? So we'll draw two plates of a two plates that conduct electricity, right? Conductive plates. And then in the middle we have dielectric. So dielectric, as I mentioned earlier, it is a component that doesn't conduct electricity. So let's imagine now we have a capacitor. So this is a capacitor, but it's not connected to any battery yet, any voltage supply yet. So what do we have in both sides? Is basically there are just plates that are in natural state, are neutral. What does it mean to be neutral? To be neutral means you have an equivalent amount of positively charged and negative charge on both sides, right? So both sides are neutral, the same amount of positively and negatively charged charges. And then what's going to be interesting is when we connect it to a voltage supply. So let's imagine now we're connecting it to, let's say, a battery, right? So a battery that has a certain potential difference. Let's say we put here the positive terminal and here the negative terminal. And as you by now know, positive terminals mean you have a surplus of energy. Negative terminals means you have a deficiency or less energy. So what happens when we are connected with a power supply? We have a terminal where there's more energy and less energy here, and it's connected to a neutral terminals on both the capacitors plates. So what will happen? Let's look at this part first, where we have a positive terminal. So here we have a neutral plate. Here we have a positive terminal. Positive terminals mean we have more energy here, right? There's plenty more energy here compared to the neutral plate. If you have more energy here than the neutral plate, what will happen? The thing that will happen is that all the electrons will circulate from the point of high energy to the point of lower energy. So here, when we compare these 2 points, here we have now what we call, if we look only into at these 2 point, here we have a negative terminal, here we will have a positive terminal. When you have positive terminal and negative terminal like this, what will happen is the current will flow from the positive to the negative. So what will happen when all the currents flows from this positive terminal to these plates? What will happen is that all the electrons from the positive terminal will be accumulated in this plate. So now it becomes a very negatively charged plate. And now let's look at this part. At this part we have a negative terminal, so it means a very low point of energy. Here we have a neutral terminal. When you compare neutral to a negative terminal, we have more energy in the neutral compared to the minus terminal. So what will happen when we have more energy here than here? The current will flow from the positive terminal towards the power supply, negative terminal of the power supply. And when it circulates in this direction, what happens is all the negatively charged, or all the electron will circulate, goes back to the negative terminal of the power supply. So we are left with only positively charged charges on this part of the plate. So if we look at the end globally, we will have lot of negative charges on this part and a lot of positive charges on this part. So now it becomes polarized and it becomes charged. So the capacitor is now what we call charged, right? So now the capacitor is charged. The next thing that is interesting to look at is what will happen if we connect it to a load. Now we're connecting it to a power supply. Now it is completely charged. When it's completely charged, what we can do is we can take off the power supply and replace it with a load. So imagine we have these plates now, which has a negative terminal and positive terminal charge now connected to a load. Imagine we have a resistor as a load. What will happen is that it will react like a new power supply, just like a battery, and the charges will now flows back into the load and consumed by the load. So now here we have more electrons, more energy. So the terminal is basically a positive terminal. So now it becomes a positive terminal. Here is negative terminals. So the current will flow back in the opposite direction of what we had just now. So all the electrons here, the excess of electrons will flow back into the right plates until both of them are balanced and again becomes neutral. So this is what we call a charging state of a capacitor, and this is the discharging state of the capacitor. So just by having two conductive plates and a dielectric material that avoid the charges to jump from one plate to another plate, we create a small battery which is called a capacitor. So in the next part, now we have seen the basic principle, the construction of a capacitor and the basic principle of its operation. Now we're going to look at a few equations that let us find the electrical parameters, usual electrical parameters in a circuit where we have a capacitor. So the first one is let's take a look at the current across a capacitor, right? So a current, imagine we have a capacitor and a current that goes across capacitor is identified as IT, and the voltage across the capacitor is identified as VT, right? Or UT. So a current across the capacitor can be identified by current can be identified as in general as the quantity of charges that circulates over time. So I equals to dq over dt, right? And in previous slides, we also know that the quantity of charges Q equals to CV, or C equals to Q over V, which means the value of capacitance of a capacitor equals to the quantity of charges that can be stored divided by the voltage applied across the capacitor. So we can say that dq can be replaced by dCV. So now we have current I equals to C dV over dt. So let's take a look at this equation for a moment and understand what does it mean. It means that, you see, we have a current which is proportional to the value of the capacitance of the capacitor, and it is also proportional to the variation of voltage across the capacitor. So what does this mean? It means that if we have a higher variation of voltage, it means if we have more difference of voltages between this terminal and this terminal, then we have a huge current that's flowing, right? That means when we are at the beginning of connection of this neutral capacitor with a power supply, right? Imagine if you connect it with a power supply, it's neutral, connected to a power supply. Now we have at this terminal a very high energy, at this terminal a very low energy. So the difference dV is very high, so we have a very high current. But what happens when dV over dt becomes 0? dV over dt becomes 0, it means the voltage across the capacitor is now equal to the voltage across the the voltage of the power supply. So if it is equal, then dV over dt is 0, so you will have no current circulating. So once it is completely charged, then the current will stop circulate. So that explains this equation of current, right? So I equal to C dV over dt. The next equation that we can look at is the voltage across capacitor. So the voltage across a capacitor, if we know the value of current which is C dV over dt, and we know that the charge Q is I multiplied by T, but now it's not just I multiplied by T. If you remember, I, the current, is dQ over dt. It's not Q over T, but it's the variation of charges over the variation of time. So we know that Q is the integration of IT dt, and plus QT0, of course, is the charges at initial condition of the charges at time 0, right? And if you know now two things that we know, I equal to C dV over dt, and Q equals to the integral of IT dt. So then, knowing that also Q is equals to CV, we can therefore write the voltage across the capacitor equals to, so it's a constant 1 over C, the integrals of IT dt, and of course plus VT0, the initial condition of the voltage at times 0, right? So that is for voltages. So two equations now that we know. The first one is the current, the second one is the voltage. So knowing the current and the voltage, we can deduce the next electrical parameters, which is the power delivered. So power, we know that power is equals to V, can be simplified as V multiplied by I, and as we know that I equals to C dV over dt, we can therefore calculate the power delivered by a discharging capacitor equals to V multiplied by C dV over dt. And then there's another thing, it's not just power, we can also calculate the energy stored by the capacitor. So energy, when we compare to power, is just the integral of the power, right? The integral of power, PT dt. So what we need to do is just integrate the equation of power, so it becomes the integral of CV dV over dt dt. So C is a constant, so we can take out C when we integrate it. So the integral of so we can cancel the dt. The integral of V dV is V square over 2. That leads us to the final equation of energy stored equals to half CV square T, or half CV square simply, right? Okay, so now that we have looked into the basic composition or the construction of a capacitor and the basic equation of electrical parameters that can be identified on on a capacitor, the next thing that's interesting to look at is what will happen. How do we calculate a circuit with where we have a configuration of multiple capacitors in it? So basically, it's just like when we had it in resistances, when they are mounted in certain configuration of in parallel or in series. The thing that we need to do is to simplify them into an equivalent resistance. So now the same case or the same thing is applied for a capacitor. So imagine we have a bunch of capacitors that's arranged in a certain configuration, and that we need to find an equivalent single capacitance. So here we're going to look at how do we do that. So just like in resistance, we will have two type of configuration or arrangement of capacitors. You can have it either in the basics are either to have it in parallel or to have it in series, and we will look at how do we reduce it into a single equivalent capacitor or capacitance, right? So in parallel, imagine if you have a circuit with 3 capacitors in parallel, C1, C2 and C3. So we have them connected to a voltage supply V, and then we have a current therefore circulating from the positive terminals goes into a node. So basically there is one node over here, and then separated into the 3 branches that we call the current separated by the node as I1 in the first branch, I2 in the second branch, and I3 in the third branch. And all the currents are gathered back into the node, a single node at the bottom, and then all the currents goes back to the negative terminal of the power supply V. Okay, so how do we know how do we find an equivalent capacitance to this? So imagine if now that we have a node, the natural thing that we would like to write down is a KCL, Kirchhoff current law. And if we write it on a node, on the node on top, we will have that I equals to I1 plus I2 plus I3. And what is I in capacitor? We've seen previously that I is C multiplied by the variation of voltage dV over dt. So for I1, it's C1 dV over dt. And for the second and third, it's the same thing as C dV over dt. Now, C are the C of each capacitor, C1, C2, and C3. But what about dV over dt? So as we know, the circuit are in parallel, so the voltage across all the branches are equal. So dV over dt are the same across all branches. Now, it means that we can factorize dV over dt. We'll have then I equals to C1 plus C2 plus C3 dV over dt. So now we see that there is a grouping of capacitors, of capacitance over here. So I, if you look at here, I equals to the sum of C multiplied by dV over dt. So this is basically, the sum of C is basically what we call as the equivalence capacitance. So we can basically redraw the circuit now as a circuit with a single capacitor, right? The same voltage V and the same current I, but now instead of having C1, C2 and C3, we have C equivalent, and C equivalent equals C1, C2 plus C3. So a remark is that if we compare it to the equivalent resistance, it is basically the opposite of it. If in resistor, if we have it in parallel is equals to the sum of 1 over, not the sum, is equals to 1 over the sum of 1 over the resistances. But now in capacitor, in parallel, it is as if it is equals to the calculation of resistance in series, right? So it's the opposite of the resistance. So just by knowing that, we can deduce that therefore for capacitors in series is the opposite of resistances. C equivalent in series equals to 1 over C1 plus 1 over C2 plus 1 over C3, right? So those are the equivalent capacitance for capacitors in series and in parallel, right? So in next part, there are basically some exercises that I would like for you to do, and then we might discuss it in a tutorial session, right? But for now, what we're going to do is we're going to go into the next part, which is inductors. Now we're going to look at inductor. So we'll start with its construction and components. So what are inductors made of? Inductors are basically a coil of wire that is coiled, and sometimes it can be coiled around a core, for example a laminated iron core like this one. So it's a coil of wire. It can be coiled around so this is a laminated iron core. It can be coiled around just a bar, or it can be coiled around a cylindrical bar like this. So it can also be coiled around air, around nothing. So there are inductors with core, iron core, or there are conductors what we call as coilless conductors, which is just like a normal coil, but without an iron core, right? So they comes in multiple shapes. The basic principle is just they are made of coils. So coils are made of basically any conductor. Usually they are made of copper wire, copper conductors, and they comes in multiple shapes. And this is what we call a toroidal inductor. So basically it is coiled around a ring. This is a usual coil, or what we call a solenoid, right? Or this one is basically a coil inductor coiled around an iron core. So this is basically a construction of the usual transformers, right? So in reality, when you look at them, they comes in various shapes and various sizes, and the basic parameters that define an inductor is what we call the inductance, right? So what is inductance? To explain what inductance is, we'll have to explain how does it operate first, the basic principle operation of it. So let's just remind a bit about, if you remember about the right hand rules on electromagnetics. So imagine if you have, so everyone knows, and we have learned this in high school, if you have a conductors where we have a current circulating in that conductors, what will happen if we will have a magnetic field, so in the direction of as what we seen in the right hand rules, right? So if we have a current circulating in a conductor, we will have a magnetic field B around that conductors. So imagine this is for a straight conductor or straight wire. What happens if we call it like an inductor? If we call it like an inductor, what happens is the magnetic field will be intensified, and they are more concentrated, right? The flux around the conductors will be intensified. So imagine if we have a coil like this, and we have a current that's circulating in this coil. So what will it create is basically it will create a magnetic flux line in this shape around the inductors, and this magnetic flux is what makes an inductor works, right? So, and then if you look at the relationship between the currents that's passing into the coil, into the inductor, and the magnetic flux around the inductor, there is a relation between them. So the relation between them is the inductance. So what we call inductance is basically the ratio of, so there is a constant n is basically the numbers of turn of the coil multiplied by the ratio of flux over current. So inductance is basically the ratio of the flux over current. So imagine if you put 1 ampere of current, the higher the inductance of your inductor, you'll have more flux around the coil. If you have a higher inductance, it means you have more flux. So a high value inductance means that your inductor can create more flux with a given current. So how do we create high flux with a certain given current, how do we create, or in other words, how do we create a high inductance? The high inductance is created by the geometry, by the construction of the inductors, right? So imagine this is our solenoid inductors in solenoid form, right? It's cylindrical. So we have different parameters. L, the inductors, depends on N square. So N is basically the number of turns of wires around or coiled in the solenoid, multiplied by mu A divided by L. So what is mu A? Mu A is basically mu R multiplied by mu 0. And mu R and mu 0 are relative permeability. So this is a relative permeability, and mu 0 is the permeability of free space. So what is permeability? So I'll let you Google what permeability is for more explanation. Permeability basically explains how much does a material conduct magnetic flux. So for example, if you look at mu 0, the permeability of free space, the permeability of free space is very, very low at 1.26 10 to the minus 6 Tesla meter per ampere turn. It means it conducts very, very low. The free space doesn't conduct very good magnetic flux, right? Permeability of core material is much higher than the permeability of free space, which means a core material will conduct better magnetic field. And well, basically that's why the reason we put a core in the middle of the solenoid, so that it conducts better the magnetic flux. And then what are the other parameters? So N square is the number of turn, mu is the permeability, mu R multiplied by mu 0. Mu R is the relative permeability multiplied by mu 0, the permeability of free space, right? And then multiplied by A. So what is A? A is the area of coil in square meters. So it's the area of the coils. And then divided by L. What is L? L is the average length. The average length of the coil. So these are the parameters that modify or influence the value of L, right? So imagine if you have, for example, if you have a bigger A, so you have a bigger diameter of your solenoid. What will happen if you have more inductance? Or if you increase the number of turns of wire, it means you'll have more inductance as well. Or if you put a material with a core material with a higher permeability, that means your mu is higher. It means your inductance will also be higher. And what is the consequence? The consequence is, if you have a higher inductance, it means you will have a higher flux if you pass a certain value of current in the inductors, right? Imagine if you put 1 ampere of currents and in an inductor with a low L, you will produce a low magnetic flux. In an inductor with a high value of L, if you put 1 ampere of current, you will produce a high value of magnetic flux. Okay, so that's what inductance is in an inductor. But how do we use it? We'll explain it by looking at the magnetic field. So this magnetic field, basically now what we have is a constant current circulating in this solenoid, and then it will create a magnetic field, a magnetic flux around it. There is a properties about the magnetic flux and the magnetic field. Magnetic field basically like to be stable. If there are variations on the current, the magnetic field will create a counter current to avoid any variation of currents. So that's the thing that we have to always remember. That's the basic principle. The magnetic field, the magnetic flux and the magnetic field, basically the magnetic field around an inductor like to be stable, and it doesn't like any disturbance. If there is variation of current, then it will create a counter current. So we'll have a look at it in the equations in the next slide, right? So some equations related to it. The first one is a voltage across inductor. Imagine if you have an inductor here, and then a current circulates in that inductor. You can measure the current, and you can measure also the voltage across an inductor. So now let's imagine if the current is a DC current. So it's a constant current, let's say 1 amperes. As we know, an inductor is basically just a conductor, a wire. It's just that it is formed in the form of a coil. If it is just a wire or a conductor, it will behave just like if there is a DC current, then there is no resistance. If the coil's resistance is very low, it can be considered that the current will go through without any problem. So the magnetic field around it will exist, but it will be constant as well. As I explained just now, if there is disturbance of current, then something will happen. So that something will happen is basically it will appear a certain voltage V across the inductors. So imagine, to understand this, imagine if you're comparing it with just a wire that has no resistance, right? If you circulate a current, a DC current, it will behave the same way. But if we change the current, if there is variation of current in a straight wire, there's nothing happen around it. But in a coil, if we change the current, then it will create a voltage in the opposite direction of it. So something will happen. Here, nothing happens, but here it will create a voltage, right? And that voltage, what is it equals? Well, that voltage is proportional to the variation of current, right? That voltage is proportional to di over dt. And the proportionality coefficient is the inductance, L, right? So Vt equals to L di over dt. So now we know what the voltage across an inductor if there is current that goes through it. And if there is variation of current, then it's L, the voltage is L di over dt. If there is no variation, then the voltage will be 0. So now what about the current? How do we evaluate the current? If we know the voltage, then the current is basically the integral. So the previous equation, V equals to L di over dt. If we want to know the current, it's V multiplied by 1 over L, and the integral of V multiplied by 1 over L. And as L is a constant, we can take out L, becomes 1 over L. So the current equals to 1 over L multiplied by the integral of Vt dt. And of course, there is IT0 here. IT0 represents the initial condition of current at times equal to 0. Now that we know the values of voltage and current across an inductor, what we can deduce next is the power and the energy delivered by the inductor. So as we know, the power is the product of voltages and currents, and we know that voltage in an inductor is L di over dt. So multiplied by I becomes Li di over dt, right? So that's power. And what about the energy? The energy, as we know, the energy is the integral of power, right? The integral of power. So the energy, we know previously that power is Li di over dt. So the energy is the integral of all of it. So the integral of Li di over dt across time. So we can cancel out dt. So it's the integral of Li di. And as we know, L is a constant. So it's just the integral of Li di. And the integral of I di is I squared over 2. So we end up with the energy delivered by the inductor, W equals to half Li squared. Right? And now, just like in capacitor, what would be interesting to look at next is if we have multiple inductors in a circuit, the thing that we would like to do is, of course, to find an equivalent inductance. So how does it work? As we know, to make it simple, we know that an inductor is basically just a coil of wire. So it acts just like a wire. So it means it can be presented as a normal resistance as well. It's just like a resistance. So just like a resistance, if you have the inductance in series, just like here, if it is in series, then the equivalent inductance is the sum of all the inductance, L1 plus L2 plus L3. And the same goes for if it is in parallel. If the inductance L1, L2 and L3 are in parallel, so the equivalent inductance will be 1 over L1 plus 1 over L2 plus 1 over L3. So that's